So good afternoon, students. In our brief session of power electronic converters, today we are going to learn about the controlled rectifier part, the controlled conversion part. Okay, so we will first see how an SCR or thyristor controls the power. Fine, and then we will simulate it. Is there anybody who is not familiar with silicon controlled rectifier or SCR? Let me know, so that I can discuss accordingly. Okay, Derek, we will see that, right? Um, so first I will start with a very basic uh, converter, that is AC supply is there, then there is an SCR, okay, silicon controlled rectifier, and then we have a resistor at the output. Input voltage is V in. The switch voltage across the switch is VTH. We call it VTH, right? And then there will be current flowing through the circuit, that will be I of t, right? Now what happens? Let us say we have just a minute. Let us say we have an AC waveform, okay. In fact, if I draw this, it will be more appropriate. Fine. So this is time. On y-axis, I have V of t as well as other signals. Now V of t, that is, or V in of t, that is shown by some dashed line. So I will draw a dashed line here. It's a sinusoidal voltage. Right? This is C, V in of t. So there is a sinusoidal voltage like this. Similarly, I can continue, and V in of t is given by Vm sine of omega. Okay. And now there is one signal which is given to this pulse. Okay. Now it's a controlled rectifier. The meaning of controlled rectifier is that it acts as a switch. Sorry. It acts as a switch, but a controllable switch. Okay. So I can represent this equivalently as a switch like this, which can be controlled from terminal G. This is terminal G, whereas other terminals are anode and cathode. So there are three terminals: A, cathode, and G. A, K, and G. The advantage of controllable switch is that you can decide when it will turn on. Okay, that means when you are going to close this switch, that is decided by the terminal G. Now, for example, in our case, we decide that the switch is going to close at this instant. Okay, so I'm going to give a small pulse which will be delayed by some angle alpha. Okay, now alpha is means it is an angle. This is alpha. Okay, which means when you give signal alpha to this G, so it is basically Vg. Okay, so then the switch will act as a closed switch. Okay, and when it acts as a closed switch, you have two modes of operation. One, there is an input voltage, there is a closed switch, and there is R. Fine. So look at this, the switch is closed, so VTH, that is voltage across the thyristor, is going to be 0 because it's a short circuit. Okay, and now this acts as a closed path, so the current I will flow. Okay, whereas the voltage is already V in. Okay, so when you measure the voltage across VR, so VR is nothing but V in, because there is no other drop in the circuit. So voltage across the resistor, that is here, you can also call it output voltage. It is the same as the input voltage, right? So then it starts. So here, the moment you apply the control signal to the switch, it behaves as a closed switch. So then you get the output voltage like this. Okay. Now when the voltage is negative, at that time the device acts as an open circuit. Remember. Okay. When the voltage is negative, that means there is no current flowing. I can draw the current here. Okay. So the current is current IR is given by VR by R, or you can say V in by R. So then the current will simply follow the voltage. Now here the current becomes 0. Okay, this is 0. So the current becomes 0. This is I. Current becomes 0, and you apply some voltage in reverse direction. Okay, so what will happen to this device if you apply reverse voltage? That means plus here, minus here. Simply it acts as an open circuit. Okay, so the SCR is one device in which it acts as a closed switch when the voltage applied to it is positive and gate signal is applied. If you do not apply the gate signal, remember, if you do not apply the gate signal, it still acts as an open circuit. Okay. So you actually have three states. One, gate signal is 0 and you apply some voltage across device. This acts as an open circuit. Okay. Now if, let us say, gate is 1, or you can say VG is greater than 0, and then you apply the positive voltage, that is plus here, minus here. So then it acts as a closed switch. But when you apply positive to cathode and negative to anode, just recall the operation of diode. Okay. What will happen? It will behave as open switch. Now G is immaterial. It doesn't matter what you apply at G. In fact, you don't apply anything, but it doesn't matter what you apply at G. Your switch will still be open. So this is open. Okay. So we have three states. We have three states here. One, if the forward voltage is applied and nothing is applied at the gate terminal, it acts as an open. Forward voltage is applied and you apply some voltage at gate terminal because of which the current flows, so it acts as a close. And you apply positive at cathode, negative at anode, that means you reverse bias it. Okay. So first two conditions are pertaining to forward biasing, and this condition is pertaining to reverse biasing. But the switch is closed in only one case, whereas it is open in both cases, those two cases. So now what happens, that because the switch is open, you have V in here, R here, output voltage is measured across the resistor. Okay, now you tell me what will be the current. What is the current in this circuit? So Karthik has given correct answer. What about others? Lemi, yes. Okay, so your answer is correct. Akash, your answer is correct. So now it is public. The answer is public. So I must say that yes, correct. The current is 0 because the circuit is open. Okay. Sorry. Fine. If the current is 0, then voltage across resistor is equal to the current into resistor. That means 0 into R, which means the current voltage across the resistor is 0. So remember, if the switch is open, the resistor is not connected to anything. So the voltage across the resistor will be 0. So here you will get 0 voltage. Okay. Now once again, this signal is applied exactly after 2 pi. Okay. The control signal is applied exactly after 2 pi, that is 360 degree. So unless the signal is applied, I am not getting anything. The moment you apply the signal, the moment you apply the signal, the switch once again closes and you get the output voltage. Okay. Now, what is the average of this? What is the rectified output? That we will see later, because it is anyway very simple, right? And it is theoretical, more theoretical. But we are more interested in how I got this output waveform, and does it actually happen in practical case? Okay. So we want to verify this. We want to verify this condition where we try to trigger the SCR, and then this SCR closes. It acts as an closed switch, and then it starts conducting the current. Okay. So let us simulate this. So I will start with a new model. Now I hope everybody is acquainted to developing a model or creating a model in the MATLAB. Derek, is this clear what I was trying to say? Derek? Is this clear? Okay, no problem. So basically this silicon controlled rectifier is a device which is a 3-terminal device, and it is on when the signal is applied at the gate terminal. If you don't apply any signal, it will not turn on. Let us see, let us verify this. Okay. That's why we are doing the simulation, so that if any concept is not clear to you, you can verify this. Okay. Okay. So I hope you can see the screen. Go to SimScap, Sim Power System, and Specialized Technology. I hope this path is clear. And then we start with the fundamental block. First, you need to bring power GUI. Okay, whether either first or last, that depends on you. Then we go to electrical sources. Now I will bring AC voltage source. Okay, I will bring AC voltage source. I will define the parameters of AC voltage source. Peak amplitude will be 230 into square root of 2. Okay, that means probably 320, you can say. Okay, I can write 320 also. Frequency will be 50 Hertz, and sample time should be set to 10e minus 6. This is just for my convenience. Okay, you can set it to 100 microsecond also. Okay, so this way I have defined the parameters of AC voltage source. Yes. You are talking about this path, right?
Yes.
What do you want to do with this path? This path, actually, you should go to this browse for folder, and you can set your working directory. Okay, for example, I want to go to D drive. In D drive, I want to set some folder for my purpose. I can set that folder later on, and then I can work in that folder. So you can set it from here, browse for folder. Okay, and then your model should be in that folder, so that it can readily find out all the files. Okay, otherwise the MATLAB will be a little bit confused. Okay, normally default it is C documents MATLAB. It is like that. Okay, so now I'm going to have one voltage source. Let us keep them side by side. I will keep them side by side. Okay. After voltage source, I need to find element. I want to bring series RLC branch, remember, series RLC branch. And then I will set it to R type, resistor type, and keep the resistance to 100 ohm. Okay, you can even keep it to 10 ohm. In simulation, it doesn't matter. Fine. The next step is to bring a thyristor. Now, there are two types of thyristors in power electronic same power system, specialized technology, fundamental block, power electronics. Here, there are two types of thyristors. One is the thyristor and the other one is the detailed thyristor. Don't go for detailed thyristor, only go for thyristor. Okay. And then double click on thyristor. Fine. Here you have on resistance, on state resistance. We keep it to 0.001. Forward voltage should be set to 2 volt. Practically it is 2 volt normally, right? Snubber resistance we will keep as it is unless we have a clear understanding of snubbers. And show measurement port will be there. Place OK. Now AC voltage source phase or plus terminal is connected to anode of the thyristor. Cathode is connected to the load, and then we complete the path. Fine. Okay. We will also have one current measurement, right? So I will go to measurement, bring the current measurement block and voltage measurement block. There are two blocks. So bring the voltage measurement block and current measurement block. Put the current measurement block in series and voltage measurement block is connected in parallel like this. There will be one voltage measurement block at source side and another voltage measurement block at the load side. Fine. And after this, we want to see the output. So we will go to commonly used blocks and bring the scope. Basically, all sync this XY graph, oscilloscope, display. If your quantity is static, you go for display. If your quantity is a waveform, you go for scope. If you want to display something, keeping one quantity on x-axis, another quantity on y-axis, then you go for XY graph. But we normally work with scope. Okay. So I will bring a scope here and there will be 3 terminals, right? First 2 terminals will be connected to voltage, output voltage, right? And then we also have the current. The current is same in the line. So I'm not going to connect a separate load current and separate source current. That is not possible here. So now I have all the quantities available. Fine. And first I need to save this document. So I will save it as a single phase half wave rectifier. Okay. I call it single phase half wave. Karthik, I will come to the pulse later. I just want to show what happens without the pulse, right? What happens if you do not apply the pulse to a CR? And then we will connect the pulse generator, right? So everything is configured. Now go to simulation, model configuration parameters, and run it for 0.1 second. I think that will be sufficient. Okay, I will come to that. And select ODE23 TB or discrete, whatever you say. Keep it discrete, no problem. Okay. Sorry, keep it continuous one. Fine. Okay. To change the register, you need to double click on register. It is actually RLC branch. You can select any type from this list. For example, I can keep it L only. If I apply, it will generate L. If I keep R, I apply, it will generate R. Okay, so it is like this. And resistance is set to 100 ohm because I want some amount of current to flow in ampere. Okay, it's a power electronics. So the current will be in ampere and not in milliampere, remember. And now I set it to 0.1, right? Let us run it. We expect something. I will keep all three waveforms separate. Fine. Now we expected that the output voltage will be available, but as you can see, very little output voltage is available. This is actually nothing. Okay, this is almost as good as zero. Okay, because we are supposed to get 300 volt. We are supposed to get 300 volt, right? And we are getting only 2 volt. That means our device is not working. And the current is also in milliamperes, which means the device is not working. So what we should do, actually, we did not apply the gate. Okay. And that's why this is happening. So without gate application or without control signal application, the device is not going to work. Remember. Okay. You will not get anything on the output. So what to do? You need to control it. Okay. You need to control this. To control the power electronic device, you need to select some kind of, you need to apply some kind of pulse. So I will go to Simulink, go to sources, and there is one source called pulse generator. I will bring that pulse generator here. You might have used this in a DC-DC converter. Have you? Have you used the pulse generator before? Right? Okay, Lemmy, are you aware of the pulse generation? Ahmed, Lemmy, Derek. And what about Toy Toy Kang? Are you aware of this pulse generator? Okay. So we will connect a pulse generator to the gate terminal of device. Fine. Now we need to configure the pulse generator properly. Amplitude is going to be 1. This is actually generated in binary logic. So either we will apply 1 or we will apply 0. If we apply 1, it will be treated as 1 or control signal, application of control signal. And if you apply 0, it will turn off the switch. So basically here, if you apply 1, it will turn on the switch, it will make it open. If you apply 0, it will keep it off. Okay, that's it. So here I want to keep amplitude to 1. Period will be equal to the frequency, remember. Okay, frequency is 50 hertz. So I will keep period to 1 upon 50 or 0.02. Fine. Pulse width should be probably 10%. Okay, it should be actually 180. It should be actually 50%, but I'm keeping it 10% here, just for your understanding. And phase delay is going to be in seconds. Now let us say I want to apply a 30-degree phase delay. Okay, so for 360-degree, it is 20 millisecond. So how much delay will be required for 30-degree? So what I need to do, I need to divide 360 by 30 by 360 and then multiply it with 0.02. So it is 0.001667. This is the delay required for 30-degree delay. Okay. Which delay I am talking about? I am talking about this alpha. This delay is 0.001666, right? So that much delay is set in the pulse generator here. Okay. And now I will see the pulse and I will also see the output. Fine. So let us skip 4 scopes here. Four scopes, right? The second should be gate pulse, third will be output voltage, and fourth will be output current. And now let us see the output. What do you see? What do you see? There is AC sinusoidal voltage, right? Then you apply a pulse which is delayed by 30-degree. So your device starts exactly after 30-degree. Okay. The moment there is a 0 voltage, the device stops conducting because the current is also 0, right? And current is just following the voltage. Resistance is 100 ohm, so voltage is divided by 100. That is your current. Is this clear? What about others? Is this clear? Okay, you're talking about pulse width. Pulse width, I set it to 10%. Even if I make it, let us say 50%, it doesn't matter. You see, there will be no change in the output. Normally it is kept 50%, but in this case, even if I keep it 50%, it doesn't change the output. Yes, in that case, we'll need it, but this is just only for fundamental understanding, okay? So practically, if you are actually designing a converter, then you should design you should design the pulse generator circuit such that you get a 50% duty cycle, okay, in the second waveform, okay. But only for the sake of understanding, we kept it 10%. Fine. Now let us make it a little bit interesting. We will make it a little bit interesting, where now I will extend this circuit and connect another SCR in anti-parallel. For example, this is SCR number 1, let us say, and this is SCR number 2, let us say. Okay. Now what I will do, I will trigger the SCR T1 during positive half cycle. This is V in. I will trigger T1 for positive half cycle and trigger T2 for negative half cycle. So the scenario will look like this. This is T. These are control signals for T1 and T2. And this is going to be the waveform. Okay. So I will start with sinusoidal waveform. Let us say this is T. On x-axis you have T or omega T, whatever you say, right? And T1 is fired here. Okay. Whereas T2 is fired here. Okay. Once again, T1 will be fired. So this angle is called alpha, and the duration between two consecutive firing is 2 pi. Whereas the duration between T1 and T2 is pi, or you can say 180 degree. This is 2 pi or 360 degree. Now this, whenever T1 conducts, the current will flow from T1 through the R in this direction. Okay. So the direction will be like this. which is shown by arrow. Okay. And whenever the T2 conducts, the current will flow in this direction. Are you getting it? Okay. So during the negative half cycle, T2 will conduct. Okay. During the positive half cycle, T1 will conduct. And now when T1 conducts, the current flows from positive to negative. So you get a voltage like this. And whenever T2 conducts, the current flows in reverse direction. So voltage drop is also in negative direction. So now you have voltage like this. Once again, remember, whenever the switch does not conduct, the current cannot flow. So for the switch is off for this much duration, for duration alpha. Okay, for duration alpha, the switch is off. Okay, so let us modify the original model, right? So I will keep, okay, extend this. But this thyristor T2 should be in reverse direction. That is the only constraint. So this is anode and this becomes the cathode. Fine. And here the pulse generator should be triggered. Yes. Okay. M means measurement. This M means measurement. That means you can measure the quantities related to thyristor. We will come to that part later. Okay. How to use M. So here, as I said, the phase delay should be alpha plus 180 degree. Okay. You look at this. What should be the phase delay of T2? It should be pi plus alpha. Okay. This is what? Pi plus alpha. Fine. So accordingly, you will set, this is alpha actually, and I add pi in it. Pi means 10 divided by 20. Pi divided by 2 into pi. Okay, into 20 millisecond. So then I will get 0.01. Okay, but if I want to keep pi plus alpha, that means I need to add 0.01 and 0.001667, right? So then it will become 0.011667, like that. Okay. So now I have changed the pulse generator delay, which is other properties are same. Only thing is that phase delay is 0.011667. And now, okay. Now I want to see both the pulses in same window. So what I will do, I will go to commonly used blocks and multiplexer. Yes. Okay. So Akash has a query how to calculate the phase delay. See, phase delay, we want to keep a phase delay of 30 degrees. 30 degrees means for 360 degree, it is 20 millisecond, that is 0.02. Then for 30 degree, it is 30 by 360 into 0.02. That means 30 degree is equal to 0.001667 seconds. Okay. So then what is 180 degree? You can calculate 180 degree means 10 millisecond or 0.01 second. Okay. So 180 plus 30, that is 210 degree. Okay. Here we want to obtain 180, that is pi, plus alpha, which is 30 degree. So 180 plus 30, that is 210 degree. I want to calculate 210 degree here. Then I will say 210 divided by 360 into 0.02. So then it will be 0.011667. So this way I have calculated the firing angle of second SCR, right? And now I will club pulses of both, right? Multiplex them. I think you are aware of this word multiplex. Multiplex means all there are n number of inputs and only one output is there. Okay, so there will be multiple input signals and there will be only one output. So all signals will be merged into one. That is the purpose of multiplex. You can decide as many number of inputs as you want using a number of inputs. Okay. And now let us see the performance. Okay. The first one is the AC voltage, which is coming at our home, domestic one, right? The second is the firing pulse, right? The third one is the output voltage, which is just like what we have drawn here, right? This is the output voltage. Fine. And then you can calculate the current also. Is this clear? Is this clear? Now I will further delay, like here I am going to keep 0.005, which will make 90 degree, 5 millisecond for 50 hertz. So that means it is 90 degree, whereas here I will keep it 0.015, right? So this will make 90 degree and then I run it again. What do you see? A completely chopped waveform. Okay, completely chopped waveform, right? Which is there for 90 degree and it is not there for another 90 degree, right? So what is the purpose of this chopping the waveform? So after you chop the waveform, let me bring something related to measurement so that I can prove it to you that this has something to do with your output. So I will bring one RMS block. Okay. Okay. I will bring one RMS block for voltage and RMS block for current. Okay. Fundamental frequency is 50. Initial RMS is 0. And sample time is 10e minus 6. Okay, as we have done in the earlier case. And I will copy this only so that I don't have to change the parameter again and again. So fundamental frequency is 50. Initial RMS value is 0. Sample time is 10 microsecond, and I kept true RMS. When true RMS value parameter is unchecked, the block outputs the RMS value of the fundamental component. I don't want that. I want actual RMS. Okay. So, okay. And go to sinks, I will bring the display. Fine. I bring the display here. As I said, for static display, you should use the display block. Okay. Now you run it again. Okay, what do you see? What is RMS voltage here? 158, right? It is not 230. See, we have given 230 RMS voltage as input, whereas on the output side we get 158, right? So RMS voltage is reduced. Basically, the RMS voltage is reduced. Okay, so this way you can control the output voltage, right? And how it will be useful? So it will be useful if I connect, instead of this resistor, if I connect a fan here. If I connect a fan here, then just like our home, okay, what we have developed is the fan regulator, remember, right? So this is fan regulator circuit, okay, in its very simplified form, right? Now because the voltage reduces, if you recall, earlier we used to have voltage divider circuit in fan regulator, but now we call them electronic regulators. So electronic regulator, in electronic regulator you control the output voltage like this. Okay, you have a kind of chopped waveform, right? You control the output RMS voltage, and because the voltage is reduced, so your fan rotates at lesser speed. Okay. Now any query related to this? Any specific query related to this discussion? In terms of control, yes, controlled rectifiers are better than diode rectifiers, because in diode rectifiers you do not have control over the output voltage that you see here. Okay, in diode rectifiers the output voltage will be constant. Okay, you cannot control the output voltage, and that is why diode rectifiers are also known as uncontrolled rectifiers, where you don't have any control over it. Whereas In a controlled rectifier, you have a complete control over the output voltage. So as long as application is concerned, yes, control rectifiers are better than the diode rectifiers. Any other query related to this implementation? Okay, thank you. So I think now we have concluded the session, and Professor Uvesh Sipai has, I think, created a separate link for you. So you can leave this session and you can join there. Okay, thank you.